Hello everyone, I am Pragya Srivastava. I am here to record a lecture on control system. The course code is KEC 602 and we are discussing the time response analysis unit 3, and in my previous lecture we were discussing second order control system, and we are going to study in this lecture the step response. Based on the step response, we will study certain parameters, and these parameters are based on time domain specifications. So we will study delay time, rise time, peak time, overshoot, and then settling time. Also some numericals. Then from here we can see that the step response of a second order system is this, and we can call it as a transfer function. So this is the transfer function. Of course, since we are giving the step input, so the value of Rs given to the system was 1 by S. So from here we can have, and we can substitute the value of Rs in the above equation, and then we can have the value of Cs. So we can see that what is the value of Cs from here. So let us substitute the value of Rs in the above equation. Now we can also rewrite this as a, and we can find out, let's say, the case 1 when zeta equals to 0. So case 1 is Rs is equal to 1 by S always, and zeta becomes equal to 0. So when zeta is 0, so this term goes off and it becomes S square plus omega n square, S square plus omega n square. So this is case 1. And then multiplying this Rs here this side, we have the given equation, omega n square upon S square plus omega n square into 1 by S. So the resultant equation is this. Of course, when we take inverse Laplace, we can have the value of Ct. So Ct from here we can see that it is nothing but 1 minus cos omega nt ut. So this is the step response, or more correctly we call it unit step response. Unit step response because here A is 1. So unit step response for a system when zeta is equals to 0. So when zeta is equals to 0, the response will be equal to Ct is equals to 1 minus cos omega nt ut for a second order system. Now here delta will be equal to 0 and it will be continuous time signal with constant amplitude and frequency. We have to see that what has been told in this last sentence, that this delta will be equal to 0 in continuous time signal and constant amplitude and frequency. So actually zeta equals to 0, it means that there is no damping, like zeta represents damping ratio. Now when zeta is equals to 0, it is a case of no damping, or we call it undamped oscillation. So undamped oscillation means the time signal will be having constant amplitude. So it will be like this. The amplitude remains constant. Of course, you can see for this signal, the frequency is also constant. We see, since there is no damping, let us consider that some damping is there. So if some damping is there, we have to go like this. So the amplitude is no more constant. Initially it's high, then it's less, then again reducing. So the amplitude is changing. So amplitude is not constant. Frequency itself is, see this frequency is also not constant. But here you see the frequency interval, they are constant. So we see constant amplitude and constant frequency. So this was Case 1 when zeta equals to 0. Now we will be studying case 2 when zeta equals to 1. Now zeta equals to 1. So when zeta equals to 1, we are here this term was 2 zeta omega n s. So this reduces to 2 omega n s. So when we write 2 omega n s, we can see a perfect square here. So we can write it as omega n square s plus omega n whole square. Multiplying rs here is this thing. So cs by rs and rs is 1 by s, multiplying that side. And then we can do the same analysis, partial fraction thing. So when we are entering into partial fraction and we are having the values of a, b, c as 1, minus 1 and minus omega n. So from here we are taking inverse Laplace here. So this will give me t, this will give me e raised to the power minus omega n t, and this will give me omega n t e raised to the power minus omega n t ut. So this is the what we call, this is the unit step response of second order system for zeta equals to 1. So here we see for zeta equals to 1. So zeta equals to 1, we cannot say that zeta is 0 and there is no damping and the system is undamped. When zeta is equals to 1, we say it is critically damped. The condition is called critically damped. Critically damped. Now case 3. Case 3 is zeta between 0 and 1. Okay. So this is a case where the zeta value cannot be removed like we have removed in the previous case, zeta equals to 0. Zeta equals to 1, we are just not writing. No, nothing like that. So we have to include zeta everywhere. You can see everywhere you have this term zeta. So zeta will now appear and show its performance for the first time. So we have to consider it. Now what is happening? To break this and simplify this term, which we are just adding and subtracting zeta omega n whole square. So this term was already there, this term was already there, and this term was already there. The two foreign term which has come into picture is plus zeta omega n whole square minus zeta omega n whole square. So we are adding and subtracting just to make certain perfect square things. So from here we see that it is a perfect square, s plus zeta omega n whole square, and then taking omega n square common from these two n's, the terms we have 1 minus zeta square. Now the value of cs is omega n square, of course. Omega n was there in the numerator always, and then in the denominator we had s square plus 2 zeta n omega n, zeta n s omega n. So then we have s omega n square upon s plus zeta omega n whole square plus omega n square into 1 minus zeta square. Now again unit step, we have rs is equals to 1 by s, and then we are multiplying rs on the RHS. Multiplying this, we have this partial fraction thing, and this partial fraction will be a plus bs plus c. Having the values and substituting the values of a, b and c, the system can be rewritten like this. Now we have to see this derivation very crucially. This is important, and once you understand it for first time, you will be able to solve it again and again. So what is happening? S plus 2 zeta omega n divided by s plus zeta omega n square plus omega n square 1 plus zeta square. So what we are next doing in this, we are separating the terms out of this 2 zeta omega n s. So once we are taking, it is equivalent to omega and zeta omega n plus zeta omega n. So we are taking two terms out of this. So one zeta omega n goes with S, another zeta omega n forms a new term. Okay, so this is the first step. Then we see that when we are rearranging, we have to see that here we have S plus zeta omega n. Here also we have S plus zeta omega n. Now, S plus zeta omega n, S plus zeta omega n square. So to make it suitable for inverse Laplace, this term needs to come in square. So to make this in square, we are writing it as omega n root over 1 minus zeta square. Look on to the second term. From the second term also, we are multiplying and dividing root over 1 minus zeta square into numerator and denominator. So once we are multiplying these two, and we already had zeta and omega n is there included in this term. And now we are again seeing that we have omega n root over 1 minus zeta square, and from this term we have S plus zeta omega n, and here we see it is again fitting into a perfect square omega n root over 1 minus zeta square whole square. We can see that the particular thing maps perfectly in the inverse Laplace in my future equations. Now we have to make certain substitution. Omega n 1 minus zeta square. We have to understand and let this be as omega d. So let us write omega d is equal to omega n root over 1 minus zeta square. Okay, I have to write it as zeta square. Now, since this is natural frequency omega n, multiplying with some impact of zeta, so natural frequency being multiplied by some impact of zeta, which is damping. Can I call the new frequency as damped frequency? Damped frequency. So damped frequency means omega d. So this substitution is like that. Omega d, which is damped frequency, is equal to omega n root over 1 minus zeta square. From here, I am writing it this term as omega d square, and also here this term as omega d square. So of course we have to convert it into we have to take the inverse Laplace. So the first term goes with 1. The second term comes with e raised to the power. So e raised to the power minus omega nt. So this is a cos function, cos omega d dt. Okay. This is of course a constant term, x. And in the second term, we see that it is going with a sine function, sine omega d t and e raised to the power minus omega n t. So this is the required output equation. Now the required output equation can be rearranged and rewritten in a simpler way. So we see from here onwards, we can see that this is the, we can call it the perfect and the complete output equation. Ct is equals to 1. So here this term from the two equations, we see that we are taking this term e raised to the power minus zeta omega n common, e raised to the power minus zeta omega n common. Also, we are taking this term also common outside, raised to 1 upon root over 1 minus zeta square. So for this term, we have to multiply it. And then for the first term, we are multiplying it. Second term, it was already there in denominator, so took it outside. So this is the reduced equation from this step to this step. Now, again, we see that let the sine theta equal to root over 1 minus zeta square. So this is any equation where we have assumed that sine theta is equal to root over 1 minus zeta square. Then we can also write it as sine, squaring both sides. So we can write it as sine square theta is equals to 1 minus zeta square, and we can also write it as 1 equal to sine square theta plus cos square theta. Or so if we can compare the two equations, we can write, let's write is, for now we write it as zeta square only. So we can see and compare it with the standard equation 1 plus sine square theta plus zeta square. We compare it with the sine square theta equation 1 plus sine square theta plus cos square theta equals to 1. So from comparing these two, we have cos square theta is equals to zeta, or we can see that zeta is equals to cos theta. Then cos theta can be substituted wherever you have zeta. So we see from here and onwards we have this term. So this term can be written as sine theta. Cos omega dt was already there, and then zeta is there. Zeta can be rewritten as cos theta, and then sine omega dt was already there. And of course, this bracket is some formula, which is nothing but sine a plus b. And this is the final and reduced equation of, having the value of unit step response for a second order system where we have damped oscillation. Why? Because zeta is not equal to 1. So critical damping is not happening. Zeta is not equal to 0, where undamped thing is not happening. So zeta is having some value. So when zeta is having some value, zeta is the damping ratio. So of course it is damped oscillation. So damped oscillation means the system will be having this kind of, or we can have so based on the particular system, we can have any kind of output. So damping means the resultant amplitude goes on decreasing. So the unit step response of a second order system having damped oscillation, that is decreasing amplitude when zeta lies between 0 and 1. So this is case 3, when we have the value of zeta in between 0 and 1. So this is the first example and the first type of diagram which we are studying. Of course, damped oscillation, we can see amplitude is also changing, frequency is also changing. Here and all frequency is less and frequency is increasing, then of course it will increase and go on increasing. Now, we have to see what is delay time, what is rise time, what is peak time, what is overshoot, what is settling time. So delay time is TD, rise time is TR, peak time is TP, maximum overshoot is MP, settling time is TS. So from the diagram itself we see that delay time means, let's say the output should be, we are considering the step input. So 50% means 0.5, step input unit step means 1. So this is the ideal output and we are reaching the 50%. So the time when the output reaches 50% of the output, that is delay time. So we call it 50% of desired. Next, rise time. Rise time, let's say the desired value is 1. Now, for different literature, we have different values. So when we reach 90% of the desired thing, we call it rise time. So here in this diagram, we can see that they have taken it as 95 or more than 95. Next, rise time, somewhere you see in some books, you see 80%, 95%. So it means when we are approaching desired. Peak time. In the complete lifespan, in the complete output, what was the time required to reach the maximum possible value? So it is the peak. It is the peak. This is peak, sorry. Maximum amplitude. It is the time corresponding to maximum amplitude. And then we have maximum peak overshoot. So maximum peak overshoot responds to the difference between the peak value and the desired value. Peak value is this, desired value is this. That is the difference. Settling time. Settling time means it is the time required for a system, time required for the system when the system settles. Settles means the same which we have studied in the steady state. When the system almost reaches the output and it stops the transient behavior. So it means the system is settled. So that is called settling time. So that was all from my side in this lecture. Thank you.